We have a statistical mechanics practice final exam, 11 free response. Let's get right into it. Number one, a system contains n equals 6 distinguishable particles. Each particle may occupy either a ground state, energy 0, or an excited state of energy epsilon. So A, how many microstates correspond to total energy? E equals 2 epsilon. So that's for part A. N equals 6 particles and total energy E equals 2 epsilon. That means only 2 particles are excited. So the number of microstates, and please pardon my omega, pardon these poorly drawn omegas, that's going to be this combination with the 6 and the 2. There's the combination formula in relation to N and R. That out of 6 choose 2. So that's going to just come down to 15. Okay. So building on that for part B, compute the entropy of this microstate. All you have to do, using that entropy formula, S equals K sub B, natural log of omega, plug in the 15 from part A, you get S equals K sub B, natural log of 15. Okay, part C, if the system instead has n equals 20 particles and total energy E equals 10 epsilon, determine the multiplicity formula. You do not need to compute the number explicitly. So if n equals 20 and E equals 10 epsilon, then exactly 10 particles are excited. Omega and then omega equals this combination formula for N and R, 20 and 10. Okay, so I'm going to go rather quickly through this because you have the setups and you can always pause the video. You can always go ahead and try everything first. Okay, so that was 1. Here's 2. So let me just get that in focus. Okay, for 2. Consider a paramagnet consisting of n non-interacting spin 1/2 particles in a magnetic field B. Each spin has energy E equals negative mu, B spin up, and E equals plus mu, B spin down. Part A, let's see, write the single particle partition function, Z. So for part A, each spin has energy going up, negative mu, B, down, positive mu, B. What we're going to do is we're going to let beta equal 1 over K sub BT. And so we're going to have a beta and a B, okay? The single particle, if you took the course, you know the difference between both. The single particle partition function is going to be as follows. Z equals e to the negative beta times negative mu B plus e to the negative beta times positive mu times B. And that's going to come out to Z equals 2 hyperbolic cosine beta mu B, that product. Okay. For part B, find the total partition function Z for n particles. So for n independent spins, Z equals, capital Z equals lowercase z to the n. So Z equals here 2 hyperbolic cosine times of beta mu B, that raised to the n. That's all you have to do for letter B for total partition. And for C, derive an expression for the average energy, okay, for that E. So doing so here for letter C down here, we're going to take that negative partial derivative with respect to beta, natural log of Z. So here, that natural log of Z, okay, when we do take this derivative, right? Okay, think of the derivative here for the Z, right? It's going to be n natural log of 2 hyperbolic cosine beta times mu times B. So what this is going to become is the partial derivative with respect to beta times the natural log of Z. That's going to be n mu B, capital B, hyperbolic cosine, take the derivative of that, that's hyperbolic tan. And then you have that beta mu b there inside the parentheses, taking the derivative of that comes on the outside, that mu, okay, and that b, therefore, what we're going to get here, the expression for the average energy after taking that derivative, remember it's the negative of that derivative, so it's going to be negative of this, negative value of this. Negative value of this one. Okay. And part D, determine the heat capacity C. Okay, so for the heat capacity C here, we're going to use C equals that partial derivative with respect to capital T of that energy. Since the energy we found is this, okay, it's this B mu B. Okay, that's going to be substituted. We're going to have a substitution here. Let x equal mu b over k sub b t. So after that substitution, take a look on how we arrive at that. Okay. We're going to let that energy equal negative n mu times b hyperbolic tan of x. So we're just changing this, becomes that. Now we're going to differentiate this. When we differentiate this, it's going to give us our heat capacity C. So C is negative n mu b hyperbolic secant squared of x, and then we have this dx dt. Okay, differentiating x with respect to capital T. So if we differentiate, we dx dt, okay, well, x is up here. If we differentiate that, that's going to come out to negative mu b over k sub b t squared. Okay, doing the calculus. And then we get C equals capital N times the quantity mu b squared over k sub b capital T squared hyperbolic secant squared mu times b over k sub b t. Okay, so and here would be our final answer down here for C. Okay, so that's all. That's for letter C, but for D. So that takes care of number 2. All right, so moving along, let's try these. It's number 3. Okay, let me just get this in focus more. A little bit more. Okay, we're good. Maxwell-Boltzmann distribution. So for number 3, part A, starting from the Maxwell speed distribution, and here it is. F of v equals 4 pi times m over 2 pi k sub b t to the 3/2 times v squared, and then you have e times e raised to this whole quantity. This e is raised to this whole quantity, negative mv squared divided by 2 k sub b t. So, starting from this Maxwell speed distribution, derive the most probable speed, v sub mp. Okay, so, Maxwell speed distribution, we write it out. Okay, now, here's what we do. To find the most probable speed, we're going to maximize this. F of v is proportional to v squared e to the negative av squared. Okay, and then we have here where a equals m over 2 k sub b t. So what we're going to do here, using calculus, differentiate this component, the d, with respect to v, d dv, of v squared e to the negative av squared. Set that equal to 0, because think maximization. We're looking for horizontal tangent line. What we get here when we use the product rule, we're going to get that 2ve negative av squared minus 2av cubed times a to the e to the negative av squared. Set that equal to 0. we could factor out a 2v, and that becomes 2v times 1 minus av squared equals 0. We're ignoring this e to the negative av squared. Think about what that would become if we plugged in the 0. So v equals 0. For 1 minus av squared, that equals 0. Add that to both sides. We isolate v squared, that's 1 over a. Take the square root. We're only going to take the positive value of it. So the most probable speed is going to be this v sub mp, square root of 2 k sub bt over m. Okay, so that takes care of letter A. And letter B, for an ideal gas, find the root mean square speed of v sub rms. So for an root mean square, in this situation for an ideal gas, this is going to be 1/2 m of that v squared, right? Times v squared, right? So this is equal to 3 halves k sub bt. Isolating this v squared, multiplying by 2 on both sides, we get 3 k sub bt over m. So taking the square root, only take the positive of it. The v sub rms is square root of 3k sub b t over m. So that's for B. And then for C, which is larger, v sub mp, v sub avg, or v sub rms. Okay, so basically the ordering is going to be smallest is v sub mp, then your average, and then your root mean square being the largest. And that's where the average here, v sub avg, that's going to be the square root of 8. Think about why that would be 8. 8 k sub bt over pi m. And think about what we had in letter A and given. Okay, so that takes care of number 3. We can move along now to number 4. Again, I'm going quickly through this. Okay. So number 4. Okay, so number 4, we have a monoatomic ideal gas contains n particles in volume V at temperature T. Part A, write the canonical canonical partition function Z sub n. So for letter A, for a classical monoatomic ideal gas, Z sub n equals 1 over n factorial times the quantity V over lambda cubed, that raised to the n, okay? Where lambda is h over square root of 2 pi mk sub b t, okay? And that lambda, that's the thermal de Broglie wavelength. So this Z sub n equals 1 over n factorial times that v over lambda cubed raised to the n. That's what that lambda represents, and we're good with letter A. Letter B, using the partition function, derive the Helmholtz free energy. We're given F for that is negative k sub b times t times natural log of z sub n. Here's what we do. Well, z sub n, we're going to substitute. We know z sub n is this. So we substitute it in, natural log of that. So natural log of z sub n is this. Now, from here, we could expand this. We're using Stirling's approximation for natural log of n factorial. Okay? So, this expanded based on using Stirling's law, Stirling's approximation. Okay, and what we're going to wind up leading to is natural log of z sub n is approximately n ln v over n lambda cubed plus n, and therefore when we just substitute, think about what could go where, and we put this f again in terms of when we just substitute f equals negative n k sub b t times the quantity natural log of v over n times lambda cubed, close parentheses, plus 1. So that's what we get for letter B. Letter C, use your result to derive the ideal gas law. So in this situation here for letter C, the pressure is P equals, and that is a negative partial to df dv. Only the natural log v part depends on v. So only the natural log v part depends on v. So we have this partial df dv equals negative n k sub b t times 1 over v. Okay, that's when we, right, taking that derivative. So thus, P is going to be N times K sub B, T over V. And then just multiplying both sides by V, PV equals N K sub B times T. Okay, so that's for C. And for D, find the entropy S in terms of F. So the entropy is S equals negative that derivative dv df dt v, using the Sakor tetrode-like form. This is going to come out to S equals n k sub b times the quantity natural log that v over n lambda cubed, close parentheses, plus 5 halves. Okay, so I skipped a lot of steps here just because, I mean, just to get through it. You could do the computation, the calculus, the algebra, whatnot. Okay. Never trust, verify, always see if your answer matches. And if there's something interesting that pops up, there's something interesting that pops up. Okay, so number 5. Consider free particles confined to a three-dimensional box of volume V. Part A, show that the number of states with momentum magnitude less than P is proportional to P cubed. So here, for free particles, the E equals that P squared over 2M. What we could say is momentum states fill momentum space. The number of states with magnitude less than P is proportional to the volume of a sphere in momentum space. That volume would be 4/3 pi p cubed. Therefore, that n of p is proportional to p cubed. Okay, moving forward to letter B, derive the density states of that G of E as a function of energy. So, since E is p squared over 2m, isolating p squared, taking the positive value of that, that would be p is square root of 2me. N of p, we know from here, is proportional to p cubed, so n of e would be proportional to 2me to the 3 halves. Okay? So, n of e proportional now to e to the 3 halves, and the density of states is g of e equals this derivative, derivative of m with respect to e, and therefore g of e is proportional to e to the 1/2. And here, more explicitly, for spineless particles, g of e would equal this. Okay. Part C, explain physically why the density of states increases with energy. Okay, so here is part C. The density of states increases with energy because higher energy shells in momentum space have larger surface area. There are more momentum states available at larger p, and since that p is proportional to square root of v, the number of available states grows with energy. Okay, so that takes care of number 5. Okay, number 6. Okay. Right here. So we have Bose-Einstein statistics. Okay, so we have a system contains indistinguishable bosons. Okay, so for part A, state the Bose-Einstein Einstein distribution function. So that's just going to be this. The Bose-Einstein distribution is that n of E equals 1 over e to the capital E minus mu over k sub b t closed minus 1. Okay, part B, explain the physical significance of the chemical potential mu. Okay, so for B, chemical potential mu measures how the free energy changes when one particle is added, and mu is that derivative, that df with respect to dn tv, right? So physically, it controls the average number of particles in the system, okay? Now, for part C, for an ideal Bose gas, the occupation number must, for part C, here's the question, why must that mu in here be less than or equal to 0 for an ideal Bose gas? Well, for part C, for an ideal Bose gas, the occupation number must not become negative or infinite for excited states, okay? And since the lowest single particle energy is usually taken as E sub naught equals 0, we need E to the quantity E minus mu over K sub BT minus 1 is greater than 0. So for E equals 0, this requires the negative mu greater than or equal to 0. And just going to tilt this last part. And mu is less than or equal to 0. So just putting that back. Divide by -1 and flip the inequality. Part D, describe qualitatively what occurs during Bose-Einstein condensation. Okay, so part D is right here. Bose-Einstein condensation occurs when many bosons occupy the ground state, and below critical temperature, the excited states cannot hold all the particles. So a macroscopic fraction enters the lowest energy state. Okay, so that takes care of number 6. Moving along to number 7. Okay, number 7, Fermi-Dirac statistics. Part A, state the Fermi-Dirac distribution function. Part A, here it is. The Fermi-Dirac distribution is that f of E equals 1 over that quantity E to the capital E minus mu over K sub B T, close parentheses, plus 1. Part B, explain the meaning of Fermi energy. For part B, the Fermi energy E sub F is the energy of the highest occupied state at absolute 0. So E sub F equals mu, and then T equals 0. Part C, at T equals 0, what is the occupation probability for states below and above the Fermi energy? Okay, here's what we have. At T equals 0, F of E is 1. For E is less than E sub F. And F of E equals 0 for E is greater than E sub F. Okay? So, all states below E sub F are filled, and all states above E sub F are empty. Okay? Okay. Letter D. Why do electrons and metals obey Fermi-Dirac statistics instead of Maxwell-Boltzmann statistics? Okay, so here, for part D, electrons obey Fermi-Dirac statistics because they are fermions with a spin 1/2. They obey the Pauli exclusion principle, meaning no two electrons can occupy the same quantum state. Okay. All right. So that's like from notes, textbooks, whatnot. Number 8, thermodynamic potentials. Okay, and this is also more textbook type note stuff. Thermodynamic potentials, part A. Define the internal energy U, the Helmholtz free energy F, enthalpy H, and Gibbs free energy G. So thermodynamic potentials are here. U is the internal energy. F is U minus TS. H is U plus PV. And G is U minus TS plus PV. Again, this is all like textbook stuff, notebook stuff. B, for this one at least. For B, write the natural variables for each thermodynamic potential. Well, the natural variables will be U equals U of SV, F equals F of TV, H equals H of SP, and G equals G of TP. Okay, so commons in between. So, and now for C, show that this differentials here show that dF equals negative S dt minus PdV. So here's what we can do for part C. Begin with F equals U minus TS. So we take that F minus 2S here. We're going to differentiate it. So that's going to be dF equals du minus TDS minus SDT. Okay? And for a simple compressible system, du, that happens to be TDS minus PDV. And we just substitute that in, okay, where we see du, and this could be dV times equals the quantity of TDS minus PDV minus TDS minus STD. And what we're going to get here is we're going to get some cancellation. The TDS's go. So dF is equal to negative S dt minus PDV. Okay? D. Explain physically when the Helmholtz free energy is minimized. So for D, the Helmholtz free energy is minimized for a system at constant T and V, at constant temperature and volume. Okay, so that takes care of number 8. And now we can move along to number 9. Okay. So for number 9, black body radiation, letter A, state Planck's black body radiation formula. Part A, Planck's radiation formula for spectral energy density per angular frequency is this. U of W capital T equals H bar W cubed over pi squared C squared times the quantity 1 over this e to the H bar W divided by, that's K sub BT, and then over, close parentheses, next term minus 1. And equivalently, here it is in frequency terms. Okay? For part B, explain the ultraviolet catastrophe and why classical physics failed. So this is, again, a textbook type thing. For part B, classical physics predicted that the energy density should grow without bound at high frequency. This was called the ultraviolet catastrophe. Okay, and the failure came from assuming each electromagnetic mode had average energy K sub B times T, and Planck fixed this by assuming energy is quantized. Okay, E equals the N times H times the frequency, nu, and C, using dimensional reasoning or known results state the Stefan-Boltzmann law. So the Stefan-Boltzmann law, again, this is textbook stuff, is that J star, okay, and that's proportional to that T to the 4th, okay, where J star is the radiated power per unit area. And for part D, describe qualitatively how the black body spectrum changes as temperature increases. So for part D, as temperature increases, total emitted radiation increases, and the peak shifts to shorter wavelengths. And this is the Wien's displacement law, that lambda sub max times T, that equals a constant. Okay, so that takes care of number 9. And number 10 is conceptual stuff, notebooks, textbooks online. Okay, stuff that good foundational knowledge. Number 10, conceptual statistical mechanics. Letter A, what is the difference between a microstate and a macrostate? Well, for letter A, a microstate is one exact microscopic arrangement of the system. A macrostate is described by macroscopic quantities such as E, B, N, P, and T. Many microstates can correspond to the same macrostate. Okay, part D, why does entropy generally increase in isolated systems? Well, for part B, entropy generally increases because systems naturally evolve toward macro states with larger multiplicity. High entropy macro state corresponds to many more possible microstates than a low entropy macro state. Part C, what distinguishes the microcanonical, canonical, and grand canonical ensembles? So here it is. The ensembles are microcanonical fixed EVN, canonical fixed TVN, grand canonical fixed TV mu. Okay? Part D, why is statistical mechanics necessary even though microscopic laws are deterministic? So here's part D. Statistical mechanics is needed because real systems contain enormous numbers of particles. Even if microscopic laws are deterministic, it is impossible to track every particle exactly, so we use probability to predict average behavior. Okay. And moving along to the last one. All right. For this practice exam. Okay, so we have our last one here. Fluctuations in the canonical ensemble show that the variance of the energy satisfies this. This change in E squared equals K sub B, T squared C sub V. Interpret the meaning of this result. Okay, so we want to show this equals this. In the canonical ensemble, the Z is this summation. Okay? And the average energy is going to be this derivative, right? Previously, before, what we're going to do, okay, we're going to differentiate again, and we're going to get this partial second derivative with respect to that beta of that ln of this lnz here. So second derivative of this, and what this is going to become is that E squared minus E squared outside. So what this is going to just become is this delta E squared, okay, is equal to that second derivative, that lnz, okay, and also this, okay, this partial with respect to beta of E equals negative that delta E squared. And what we could do with this, since beta is 1 over K sub bt, we have this d, if we take the derivative of that, dB dt, that is negative 1 over K sub bt squared. And now also that C sub B, that's the d dt, that partial of E. So using the chain rule, C sub V equals d over d beta E dB dt. Okay, that's CV here equals that partial negative delta energy squared times negative 1 over KCB T squared. Okay, so we're just substituting here, right? We already found this, right? Okay, we already found this, right? Just substituting here and here. And we get C sub V is this delta E squared over K sub B T squared. The negatives cancel out, right? And here's our final answer for that component, for the mathematical component of this, right? Now, from here, what we can say is, because we've isolated this delta E squared term, right? We multiplied by that K sub B T squared on both sides. And now we can interpret the physical meaning of this result. Conclusion, this means that the heat capacity measures how strongly the system's energy fluctuates in contact with a heat bath. And larger heat capacity means larger absolute energy fluctuations. Okay, so that was a practice exam for statistical mechanics. Hopefully it could be used as a supplement just to get you some extra problems to help you get ready for an exam. It's just a supplement, and hopefully it helps a bit. And thank you very much, and have a great day.